So this is the DicroticNotch right here, and it's a little bit of an anomaly that what's happening here at this dotted line is that the aortic valve is closing. So the big question is, why does this happen? Why did it go? Why did the pressure go up in the aorta? And I should have asked that before I started talking. But where are we? We are in the aorta right here. This is all about the aorta. So anyway, so why does pressure go up slightly after the aortic valve closes? And this is the reason why. So if this is the aorta and blood is being pushed into there from the left ventricle, then what happens is as the left ventricle is ejecting blood into the aorta is expanding, it's getting bigger, and the reason why it's getting bigger is because of compliance. And if you have it, and here's the compliance equation right here. And as you've probably learned by now, compliance is a big thing. So because of the compliance, some of the energy that's being put into the blood, if you remember, the work of the stroke work is the definition of the physics definition of work is it's energy that's being put into matter. So what happens is the energy is being put into the blood, and the blood is moving now. So now we have we have kinetic energy. That kinetic energy is converted into potential energy, and the way that happens is the aorta is elastic, and it expands. And so the reason for the dicrotic notch is that after the aortic valve closes, the aorta snaps back a little bit because of its elasticity, and that's why you get this right here, the dicrotic notch, that where it goes up. So that's a good thing to know about. Okay, and then the next thing is the application of that, and it has to do with compliance, and it has to do with aging, and generally as people age, their blood vessels get a little bit harder, and so the pressure and the flow reflections happen faster. Okay, that's just something to remember, and it kind of makes sense. If you had a lead pipe and you started banging on the end here, the vibrations are gonna come back, are gonna be transmitted much faster. That's kind of the way I think of that with compliance. But there's a clinical aspect to the aorta stiffening, and that's this. So this is the normal right here, a normal individual right there that I just circled. And as the aorta hardens and as compliance goes down, the pressure reflections come back faster. And so this is the way it should be in a normal individual, but a person with a less compliant aorta, the pressure reflections come back earlier, and you get this peak right here, and this peak actually should be drawn a little higher, maybe like that. And then you don't get this this right here like this. So and the really important reason for why you need this shape is because of the coronary arteries. If you remember, the coronary arteries, they transfer blood to the heart muscle when the heart's not contracting, because when the heart is contracting, they're not open, they're closed. So that's the problem clinically with losing compliance in the aorta, is that one is this peak right here. This is going to be higher than it should be. So that's so blood pressure is going to be higher than what is measured on the arm, and because you can't really measure. You can't measure this very easily. You can stick a catheter in there, but that's very difficult to do. But you get the wrong idea about blood pressure on the arm, because this is really what it is the pressure in the aorta. So there's a stroke risk is what the problem is with that is unknown. And then so what's the problem here? What's the problem by not having this curvature here? Instead you go like this. The problem is that the coronaries do not get perfused like they should. They get perfused less. Remember, perfusion is pushing it's pushing blood through the arteries, and so that is ischemia. The word ischemia means lack of blood flow, and sometimes it gets confused with hypoxia. And hypoxia, it's almost the same thing. It just means lack of oxygen in the blood. So they both do the same thing, but lack of blood flow, lack of oxygen. So anyway, that's the problem. And the compliance equation, that's the other thing on here, is a good thing to remember: the change in volume divided by the change in pressure. So for every amount of pressure that changes, how much volume do you get? So that's the definition of compliance.